the nuclear band of stability. We're going to look at the note which describes the nuclear band of stability, and we will follow it up by looking at the graph. Within the nucleus, there exist protons. These protons, having positive charges, will repel each other. This is why neutrons exist in the nucleus. They help to overcome these repulsive forces. This is what keeps the nucleus stable. However, in observing elements, it is seen that only elements with a proton number of up to 84 actually have a stable nucleus. Let's refer to these as the stable isotopes. Now, these stable isotopes have a stable nucleus, hence they are not radioactive. They do not release radiation by decay. However, the isotopes which are unstable, we refer to them as radioactive isotopes. Once again, to clarify, these radioactive isotopes are the ones with more than 84 protons, and they are unstable, and they therefore decay and release radiation. That's why we call them radioactive isotopes. We're going to take note of the last line because it pertains to the graph. It says, as atomic number increases and the number of protons increases in the nucleus, the number of neutrons must increase. Nuclei which are stable, that is non-radioactive, need to have a ratio of neutrons to protons between a 1-to-1 ratio to a 1-to-1.5 ratio. I've given some atomic numbers in the note. You can pay attention to them as it pertains to the graph, but you're to keep in mind that the ratio of isotopes with a proton number of up to 84, that the ratio of the neutrons to protons must be 1-to-1 to 1-to-1.5. When we do a plot of a graph, which is neutrons versus protons, all these stable isotopes, if we plot it, they're going to form a band, and that band is what we call the band of stability. Any other isotopes that do not fall within this band are called radioactive isotopes. The significance of this band of stability is that through alpha or beta decay, which will change the atomic number of the radioactive isotope, it allows the radioactive isotope to become stable, that is, form a stable isotope, and hence approach this band of stability. Let's look at the graph. Here is the plot of the graph which shows the band of stability. It is a plot of the number of neutrons versus the number of protons, and these blue dots here represent the band of stability. I'm going to explain the two other lines seen on the graph. We see a red line which corresponds to a 1-to-1 neutron to proton ratio, and we see a green line which corresponds to a 1.5-to-1 neutron to proton ratio. So if you look at any point on, let's say, our red reference line, we're going to see a 1-to-1 ratio of neutrons to protons. This is 50 to 50. And on our green line, let's say we have a 90 to 60 ratio, which is a 1.5 to 1 neutron to proton ratio. What is the significance of these two reference lines? We're going to look at our band of stability up to atomic number 20, which is here. We see that these stable isotopes have a 1-to-1 neutron to proton ratio. And for isotopes between atomic number 20 to 84, we see that the neutron to proton ratio deviates from 1-to-1 and approaches 1.5 to 1. That is why we say these stable isotopes have a ratio between 1 to 1.5 neutrons to protons. So they are stable isotopes. Any other isotope, and I'm looking at isotopes with an atomic number greater than 84 that do not fall within the band of stability, we call these radioactive isotopes. And we say that they approach the band of stability, right? And the approach to the band of stability is done through alpha or beta decay. This alpha or beta decay will decrease the number of protons, or maybe even the number of neutrons, such that the radioactive isotope forms a stable non-radioactive isotope, and this occurs through some sort of release of radiation, example, alpha or beta particles.